Greetings and welcome to the complete lecture for Chapter 16 of Chemistry 223. In this chapter, we're going to look at what's called electrochemistry. Electrochemistry is the study essentially, and most probably importantly, arguably, of batteries. And wow, right now I am using all kinds of batteries. I'm using a battery in my computer that I'm using to record it. I'm using a battery in my microphone that I'm using to record my audio. My iPad here that I write notes on has a battery. Lots of batteries all around us all the time. But it's more than just batteries. So for example, electric cars you see there in the lower left-hand corner, electric cars are great because there's no greenhouse emissions. You have to recharge them and stuff, of course, but they can be a really nice alternative to the problems we're experiencing with greenhouse gases. But also in addition, there's a lot of electrochemistry that goes on in our bodies. And without this, we wouldn't be able to live and breathe and all kinds of things. So it's a pretty cool chapter. Let's check this out and see what this chapter has to offer us. Most of the reactions we've looked at so far have involved transferring of an atom or a group of atoms from one species to the other. So in the reaction that's shown right there, acetic acid, which gets the symbol HOAC, acetic acid reacts with water to make the acetate ion and hydronium. This is a reaction we looked at in chapter 14 quite a bit. It's a weak acid, you've got some hydronium, etc., etc. However, the important part for us right now is that the hydrogen from acetic acid is being transferred to the water. It makes hydronium and then also the acetate ion. And most of the reactions we've looked at up till this point have been this way. But in this chapter, we're going to look at what's called electron transfer. And in electron transfer, you may not see the atoms change at all, like in this example right here. In this reaction, copper metal, which is copper solid, reacts with two silver plus ions, which are dissolved in water, to make copper 2 plus ions, aqueous, and two silver metal atoms, two silver solids. And that's what we're going to focus on here. Now notice that copper and silver aren't coming together, transferring stuff like that, but copper is going to copper 2 plus, so copper solid, copper with as a metal, is going from a 0 charge to a positive 2 charge, and that can only happen if copper has lost electrons. Remember, electrons are negative, so the copper 2 plus is more positive than the copper. That means the copper metal has lost electrons, becoming more positive. But likewise, the silver plus becomes silver 0 as silver metal, so the silver plus has to gain electrons in order to become silver metal. So you can see the electrons here are being transferred essentially from the copper to the silver plus. And in the process, you end up with copper, which is more positive, copper 2 plus, and silver, which is less positive, i.e. silver 0 or silver metal in this case. So these are going to be the kind of reactions we're going to look at in this chapter. You can break the copper-silver reaction down into what's called a half reaction. And in a half reaction, you're allowed as a chemist to show electrons. Now, you don't normally show electrons as a chemist. You try and keep those hidden away. But in electrochemistry, it can be super helpful to write these reactions as half reactions. So to write a half reaction, you want to put, for example, the copper species together, and you want to put the silver species together. Put the species which are somewhat similar to each other together. So in this part then, you'd have copper going to copper 2 plus, and again, copper can only become more positive if it loses electrons. So to become a positive 2, that means it has to lose 2 electrons. So you could write this as copper going to copper 2 plus and 2 electrons. And with the silver, you can do similar process. You can take the silver plus and make silver metal on the product side. That can only happen if the silver plus gains an electron. Now, because there are 2 silver pluses and 2 silver metals, we can write 2 silver plus 2 electrons makes 2 silver metals. So these would be the half reactions for this particular process. Now, the note at the bottom is important. I think all of you at this point are really good about having a balanced reaction. So the atoms on the left equal the atoms on the right, the reactant atoms equal product atoms, all that kind of jazz. But it's also important to realize that these reactions should be balanced for charge as well. And all of the reactions on this page follow this process. So if you look at the main reaction right there, which is copper and 2 silver plus going to copper 2 plus 2 silvers, on the reactant side, copper solid, copper metal doesn't have a charge of 0, and the silvers, there's 2 of them, 2 times positive 1. That means the whole reactant side has a positive 2 charge. On the product side, the copper 2 plus has a positive 2 charge, and the 2 silver metals have no charge. So you've got a positive 2 on the reactant side and a positive 2 on the product side as well. This reaction is balanced for charge and mass, and you can do that for any of the reactions we're looking at on this page or any of the reactions we've looked at in general. We haven't dealt with the charge so much because it hasn't been as important, but in this chapter it will. Keep that in the back of your mind. All of the reactions should be balanced for charge and mass both. When you have electrons being transferred in a chemical reaction, they're referred to as oxidation reduction or redox reactions. And we looked at redox reactions back in Chem 221 briefly, but we're going to do a better job right now. So these redox reactions can result in the generation of an electric current, like it's going from some chemical species which is creating the electrons to the species which is accepting the electrons. And along the way, you're going to have moving electrons. Moving electrons is essentially what electric current is. So this field is often called electrochemistry. It's using chemicals in order to enact chemical change through electrons being transferred, and it is a type of system. Now, a battery is essentially electrochemistry. It's basically two chemical parts. One part is creating the electrons, and the other part is accepting the electrons. And if you can control this, you can control the battery, which of course is so important for our lives. When you talk about redox reaction, you must know these terms. The two most important parts probably are oxidation and reduction. So an oxidation means that electrons are being lost, and reduction means the electrons are being gained. And oxidation and reduction are usually relative to the reactants, not the products. We'll talk about that. Now, as a species loses electrons and is oxidized, you see an increase in the oxidation number or the charge on the metal. We'll come back to this in a little bit. And likewise, reduction, when you gain electrons, you're going to have more negative charges added in, so the oxidation numbers will decrease, become more negative, if you will. And if that wasn't enough, oxidizing agent is another term for something that's reduced. And reducing agent is another term for something that's been oxidized. And I am just perplexed that these kind of definitions exist. Apparently, the idea is that an oxidizing agent is a chemical that allows another species to be oxidized while it itself is reduced. And reducing agent, same thing. It's allowing something else to be reduced while it itself is oxidized. And again, I have no idea why these definitions were created. I am just the messenger here. I did not create these rules. But anyway, keep that in the back of your mind. Have I introduced you to my friend Leo the Lion? And Leo the Lion says, "Grr!" And no, your instructor has not completely lost it, probably partially, but not completely anyway. This is an acronym. Leo says GER. Leo stands for lose electrons oxidized, and GER stands for gain electrons reduced. So if you look on the zinc and the copper 2 plus there on the middle left, zinc is losing 2 electrons to become zinc 2 plus, so zinc is being oxidized. We would call zinc the reducing agent here because it's allowing other things to be reduced while it itself is oxidized. And likewise, copper 2 plus is gaining electrons to become copper metal. Copper 2 plus is being reduced. We would say that copper 2 plus is the oxidizing agent here. Copper 2 plus is being reduced, and it's allowing something else to be oxidized. Leo the Lion says GER is my favorite expression, but you can also use things like oil rig. Oxidation is losing, reduction is gaining. You can use any of these kind of acronyms you want, but you need to know when something is oxidized and reduced, and likewise reducing agent, oxidizing agent. If you have a cooler saying than oil rig or Leo says GER, let me know. But I'll be referring back to Leo the Lion says GER just as we go through this section. Here's a question you might see. Which species is being oxidized in the following reaction? And you can see there's nickel, silver plus, nickel 2 plus, and silver metal. And then it says not a redox reaction. So let's start with the easiest one. Notice how nickel is becoming more positive on the product side, nickel 0 to nickel 2 plus. And notice how silver plus is going to silver. So it's going to a less positive state. So one part is being more positive, one part is becoming more negative, this is definitely a redox reaction. So answer E is out. The other thing about oxidized and reduced is they always refer to reactants. It won't refer to products. So if the answers, E is not right. Silver and nickel 2 plus are both products, so that's not going to be correct either. It's going to be nickel or silver plus. Now, oxidized is the Leo in Leo says Gur. Oxidized is lose electrons oxidized. So you want something that has lost electrons. And remembering that electrons are negative, that means you want something that's more positive. So if you look at this reaction, nickel going to nickel 2 plus, nickel is becoming more positive. Nickel can only go to 2 plus if it's lost 2 electrons. Likewise, silver plus here is going to silver 0. So silver plus is becoming less positive, more negative. Silver plus is going to be gaining electrons. So here, because nickel's becoming more positive, it is losing electrons. Nickel is being oxidized. Silver plus is gaining those electrons to become silver metal. It's becoming less positive, more negative, all right? That's why it is being reduced. And in a redox reaction, you always have to have something being oxidized and something being reduced, unless they're half reactions, but most of the time people talk about the full reaction, and then you will have something oxidized and something reduced.
Copper metal reacts spontaneously with a solution of silver nitrate. A coating of silver metal forms on the copper, while copper 2 plus ions, which are blue in water, are released into the solution.
This is an example of what's called a direct redox reaction. Direct redox reactions are great when you want to have the oxidized species and the reduced species in contact with each other. You usually have really high % yields, and it's usually fairly easy to separate out the products, which is cool. So in this reaction, they're taking copper metal, which is copper solid. They're adding 2 silver plus ions to it per copper. That's the silver plus aqueous. And they're ending up making copper 2 plus aqueous and 2 silvers. So if you look at that video at the end there, there's 2 things that are really interesting. First of all, there's that kind of mossy stuff over the copper. That's the silver. Silver in an unpurified form does not look like silver of a necklace. All right, it looks kind of like moss. All right. And anyway, that's the pure silver being made. Also notice though that there's a blue color. The blue color is indicative of the copper 2 plus ion being created. So these are just great examples of how you can use oxidized and reduced species to make things happen. And if you wanted the silver metal, you could essentially scrape it off the remaining copper and then collect it, purify it, and stuff like that. And you know the reaction was occurring because of the blue color of copper 2 plus. But also notice that the reaction happened right on the copper metal center. All right, that piece of wire, the copper wire that wound around, that's where the reaction took place. Direct redox reactions occur right at the place of where something's being oxidized or something's being reduced. So we won't get useful current out of this. We'll talk about current in a little bit, but you do have really high yields. You'd get pretty high yields of silver metal out of this one as an example. This picture shows it in more detail. On the left-hand side, you've got the copper wire in the beaker without any silver plus. And then in the middle, they've added the silver nitrate. AgNO3 is a pretty common reactant to add in these kind of situations. And what happens is the silver comes in contact with the copper metal. So the copper ends up giving up electrons to the silver. The silver becomes a solid silver metal, and the copper 2 plus ions go in solution. So on the far right-hand side, you can see there's a lot of the white atoms. Those are the silver atoms now that are connected to the rest of the copper metal. On the other hand, there's a lot of the kind of goldish looking ions floating in solution. Those are the copper 2 plus ions that have given up their electrons. They're floating around in solution, and that's what gives it its blue color. You can also, though, have what's called an indirect redox reaction, and that's what we're going to talk about a lot in this section. So in an indirect redox reaction, it allows the scientists to have some control over when electrons start flowing and when they don't. And what you basically have to do in a nutshell is you've got something that gives up electrons, the oxidized part, and you've got something that accepts the electrons, the reduced part. But what you do is you separate those 2 parts with a wire. So it's like you have have two different compartments, if you will, and the wire kind of separates them. So when you connect the wires, then the electrons start flowing. And you can see in that little animation lower left, when the wire's connected, the little light bulb comes on. So this is an example of an indirect redox reaction. A chemist has control over when electrons flow, and this is the idea behind batteries. So for example, if you're flipping channels on the TV, you don't want the remote control to be on all the time. You just want to make things happen when you press the button. Well, pressing the button completes the circuit, electrons start flowing, and that's what allows you to change the channel, turn the volume up or down or something like that. So an indirect redox reaction provides a whole nother level of power, if you will, to what a chemist can do with a redox reaction. And again, you have to set up some kind of a wire system to make this happen, and we'll talk about the particulars here in a little bit. If you look in the animation, there's a negative and a positive, and remembering that electrons are negative, they want to run away from the negative side and run to the positive side. Opposites attract and same charges repel. So the electrons will go from the negative to the positive. And I encourage you to look, if you have one, a AA or a AAA battery, maybe at home, and you should see little positive and negative terminals on them. And now you know that electrons are coming from the negative side, and they want to move to the positive side, but they'll only do that when this circuit is complete. So when you put a battery in your remote control, nothing happens until you push one of the buttons for turning the volume up or something. That starts the circuit and gets the electrons going. Pretty cool. So these electrochemistry reactions are very powerful. Batteries by alone is just a fantastic process. We use batteries for like everything these days, and batteries are essentially the control of a chemical reaction where you have something being oxidized and something being reduced. Corrosion is another good use of these redox reactions, especially like in the Navy and in merchant marine ships. The seawater is really corrosive, and they need some way to fight that, or else their hulls would start rusting all the time. So they can find an appropriate metal to like kind of take away the corrosion first. It's a big time part. But even if you have just a car, the car gets rusty, especially if you're near the ocean after a while. You can then use these techniques then to fight the corrosion and keep your car in better shape. A lot of the chemicals that we use at Mount Hood come from electrochemical processes, and a lot of the soft drink containers that have aluminum for like cans, all of that aluminum had to be made through redox reactions. Aluminum metal is not found in the wild. You only have aluminum 3+. However, if you take that aluminum 3+ and add electrons to it, you can make aluminum, and that's going to make all the aluminum we have in cars and we have in cans and all kinds of other uses for it. But it's more than just aluminum. Sodium hydroxide and fluorine and lots of the different chemicals we use come this way. But probably more important, I guess, than anything is that it's used in our bodies. And you've probably been breathing right now. If you haven't, start breathing, okay? But anyway, breathing is actually a type of a redox reaction. In our bodies, we have the heme group, which is an iron center kind of, and it takes an oxygen from the air and binds it. And then the heme goes through our bodies, and the oxygen is released later on in a place that needs it. This is a type of a redox reaction. It's a biological redox reaction, and these are also really important. So we need to talk about these and see what kind of control we can have, and also figure out how we could set one up if we wanted to. An electrochemical cell is basically a fancy type of chemical system where you have something being oxidized and something being reduced. But instead of putting them in contact with each other, we somehow have a way to control the reaction. It is usually through a wire, all right? So an electrochemical cell is just a fancy way to have at least the possibility of control over your chemical reaction. Now, believe it or not, there are two types of electrochemical cells that are possible. And the one we're going to talk about the most is called either voltaic or galvanic. And those are just product-favored electrochemical cells. So you put them together, you put them in your remote control, and they work, all right? If you're going to have a product-favored reaction that's going to create electrons, voltaic and galvanic cells are product-favored. They are batteries that work, and that's what we're going to talk about a lot in this section. However, you can have a reactant-favored reaction. So you put your chemicals together and nothing happens. Those are called electrolytic cells. They need what's called electrolysis to make any chemical change happens. We'll talk about this towards the end of this chapter, but those won't happen unless you apply electric current. And they do have utility, which is absolutely crazy. So voltaic and galvanic is just an electrochemical cell that works as is, but if you have a reactant-favored reaction, then you need to have electricity go through it. It's called an electrolytic cell. Famous electrochemists through time include both Volta and Galvani. They were both Italian, and they were both, wow, check those dates out, both early 1800s, late 1700s, stuff like that. And they did a lot of this work we're going to talk about on electrochemistry, which is just fantastic. However, my favorite electrochemist of all has to be Dr. Frankenstein. If you know about young Frankenstein, which is what this picture comes from, you'll know what I'm talking about. If you don't worry about it. Of course, Frankenstein was created supposedly through electricity, etc., etc. Frankenstein's correction from the Young Frankenstein movie is pretty funny. Anyway, you don't have to like any of my movie references or music references to get an A in my class, just so you know. But anyway, let's move on to actual chemistry. So to make sense of all the reactions we've talked about so far, we first need to be able to balance a redox equation. And this isn't a hard thing to do, but it is an important thing to do because like other balance reactions, you have to know how much of each reactant you put in, and you need to know how much product is going to come out, all that kind of stuff. So this reaction down there is an example of that. It's permanganate, MnO4-, reacting with iron 2+ and a little bit of acid, H+ is added, and the products are manganese 2+, some iron 3+, and 4 waters. So this is an example of a redox reaction. Notice how iron is going from a +2 to a +3, more positive, but the manganese is a little harder to tell. However, if you remember from Chem 221, we talked briefly about what's called a redox number or an oxidation number. And if you want to find out what the oxidation number is of the manganese in permanganate, MnO4-, what you can do is say, all right, the oxidation number of manganese plus 4 times the oxygen's oxidation number, all of that together equals -1. So oxygen's usually -2, -2 times 4 is -8, and -8 from the oxygen plus manganese equals -1. So when you do the quick math there, that's manganese plus 7 in permanganate. And that's all well and great and stuff, but we can use this +7 to confirm that this is a redox reaction. So remember, something has to not only lose electrons, but something has to gain electrons. So if you look at the manganese and the iron on the other side, you have a different story. Manganese is a +2 on the product side, while it was +7 on the reactant side. And the only way manganese can go from a +7 to a +2 is by gaining 5 electrons. So in this case, manganese is gaining electrons, it's being reduced. But something has to be oxidized as well. And you can see there iron 2+ is going to iron 3+. That's going to create 1 electron. The 5 that's in front of the irons is just to make the manganese happy. You need 5 electrons created to make permanganate go to Mn2+. So this is an example of figuring out how to balance a reaction using oxidation numbers, but I'm going to show you an alternate way here that you don't really need to use the oxidation numbers. We'll talk about that here in a little bit. But redox reactions are pretty cool. Here's a video of permanganate, that purple solution on the left, reacting with iron 2+ on the right, and they're going to make the manganese and the iron 3+.
The purple solution is aqueous potassium permanganate. The colorless solution contains iron 2+ ions. When we combine them, a redox reaction occurs. The permanganate ion is reduced to manganese 2+, and the iron is oxidized to iron 3+ ion.
You can see how the purple from the permanganate is now gone, so there's no more MnO4-. And on the product side then, that weird looking liquid there, you've got manganese 2+, which is essentially colorless. Iron 3+ has a very slight yellow tinge, and that's what I see in that beaker. Not a very strong color, that's for sure. However, you can tell that a reaction happened. This is permanganate and iron 2+ going to manganese 2+ and iron 3+. So let's look at some rules as to how you too can balance a redox reaction, it's not too bad. Let's check it out. In this question, we want to know the oxidation number of the vanadium ion in VO2 plus 1. So that's a vanadium, that's 2 oxygens, and overall a plus 1 charge. And you can see the possible charges right there. Well, to answer this one, in Chem 221, we talked about how the sum of the oxidation numbers equals the charge on the ion if there is one. So for this problem, what that means is the oxidation number of the vanadium plus 2 times the oxidation number of the oxygen, which is minus 2. All of that together equals plus 1. That's the charge on the ion, so that's why I'm letting that equal plus 1. So it's like the vanadium oxidation number plus 2 times oxygen equals plus 1. And in Chem 221, most of the time, hydrogen is positive 1, oxygen minus 2, which we'll use here. Fluorine's always minus 1, etc., etc. Anyway, if we put in here that the vanadium plus the 2 oxygens equals plus 1, and oxygen is minus 2, you can see that the vanadium's oxidation number, you can think about it like as an x. And x minus 4 equals plus 1. So you put the negative 4 on the other side is positive 4. The vanadium here comes out to be positive 5. So the sum of all the oxidation numbers in a compounder ion equals the charge, if there is one. In this case, that means vanadium plus 2 times the oxygen equals plus 1. Oxygen's almost always minus 2. Solving for the vanadium, positive 5.
Copper metal reacts spontaneously with a solution of silver nitrate. A coating of silver metal forms on the copper, while copper 2+ ions, which are blue in water, are released into the solution.
This is the reaction we looked at earlier where copper metal reacts with silver ions to give copper 2+ and silver. And I'm going to use this as an example of how to balance a redox reaction. Now, truthfully, this is a reaction you could probably balance on your own. It's not too hard. However, it's going to give me a chance to talk about the rules for balancing redox reactions. And if you use these in more complicated examples, you're going to do great. So follow along with me, bear with me. Let's see how we would balance this reaction using these rules. So the first thing you want to do is you just want to divide the reaction into the half reactions. One will be oxidation and one will be reduction. It doesn't really matter if you know what's being oxidized and reduced. But what you do want to do is you want to put like species together. So in the upper right-hand corner there, I've got the general reaction. It's copper and silver plus making copper 2+ and silver. That means you want to put the copper species together and you want to put the silver species together. So I'm going to write copper going to copper 2+ and silver plus going to silver. Now I know, and you can probably figure out that copper is being oxidized and silver plus is being reduced, but you really don't have to worry about that right now. I'll talk about that here in a little bit. So you got the two like species kind of separated into half reactions. Next thing to do, you want to balance them for mass. So you want to make sure that the atoms of copper are the same on both sides and the atoms of silver are the same on both sides, and they are. This one's so simple you don't have to do anything. But sometimes it won't be that simple and you have to balance it. We'll talk about that more later too. But anyway, this is balance for mass. The next thing though, we're going to balance them for charge. And balancing for charge can only happen by adding negative electrons. So in step 3, you want to add negative electrons to the more positive side of the reaction. So as an example of this, copper and copper 2+, copper 2+ is more positive than copper. We're going to add 2 electrons to that side. And you can see then, sure enough, copper 2+, which has a positive 2 charge, and 2 negative 1 electrons, all of that goes to 0, and that's what the charge is on the reactant side for copper metal. So that's how you balance for charge. You can only add negative electrons. We'll do the same thing with the silver. We need to add an electron to the reactant side, positive 1 plus the negative 1 of the electron. That all goes to 0, and that's what the charge is on the product side. So silver is the product, silver plus and 1 electron are the reactants. And notice at this level, we've got one species where electrons are products and one species where an electron or electrons are reactants. And you should always see that here. If you don't see it, something is wrong, all right? So in this case, your copper is losing electrons. It's being oxidized, and your silver plus is gaining an electron to become silver. Silver plus is being reduced. So the oxidized and reduced parts will come out naturally if you've done it right at this step, and you don't have to think back in step 1 or step 2 like what's being oxidized or reduced. All good reactions don't show their electrons. So this step, we want to multiply both of those half reactions by whatever we need to, so that when we combine them, the electrons will cancel out. So the copper going to copper 2 plus and 2 electrons is fine, but if you remember, the silver plus only gained 1 electron to become silver. So if we combine those as is, the electrons wouldn't cancel. So let's multiply the other reaction by 2. That means 2 silver plus reacts with 2 electrons to make 2 silver metals. And now you can see that in the reducing agent part, we have 2 electrons as products. The oxidizing agent part, we have 2 electrons as reactants. So when we add those reactions together, the electrons are out of here, which is important in my chemistry world. So the final step is literally just to add them together. 2 electrons as products, cancel 2 electrons, which are reactants. You've got copper and 2 silver plus, making copper 2 plus and 2 silver, and everything is hunky-dory. However, let's say you get to this part and you're like, oh man, not feeling good about it, man. That's okay, all right? You can absolutely make sure that the reactions are balanced for mass and charge at this point. So for example, for mass, 1 copper metal, 1 copper atom on the product side, no problem. 2 silvers make 2 silvers. So this reaction is definitely balanced for mass. The number of atoms on both sides are the same. But you can also check yourself for charge. So the copper on the left side is 0. Don't have to worry about that. The silver plus is positive 1, and there's 2 of them. So the whole reactant side is a positive 2. And on the product side, the 2 silvers don't have a charge, so there's 0. There's a positive 2 right there. The product side is positive 2. So this reaction is balanced for charge as well as mass. And again, you can always check yourself if you're feeling uncertain. And I do this a lot myself. So it's a nice thing just to double check, make sure you're good to go. The next example we're going to use involves vanadium. Vanadium's a really cool element. It's named after, I believe it's the Swedish goddess of beauty, Vanadis. I probably am saying all that wrong and incorrectly, but anyway, vanadium is a beautiful metal because it creates just a ton of different colors. So these are just some examples of some vanadium solutions, and you can see it's yellow and blue and green and purple. Oh man, vanadium is pretty cool. So anyway, we're going to use vanadium, not for its color, but for what we can do to learn about balancing redox reactions. In the second example, we're going to balance this reaction in acidic solution. So let's come back to that in a little bit. Now in this reaction, we have VO2 plus 1. That's a vanadium, 2 oxygens, and a plus 1 charge. And it's reacting with zinc metal, zinc by itself. It's going to make VO2 plus. That's a vanadium and 1 oxygen with a 2 plus charge. And it also makes zinc 2 plus. Okay, so like before, we're going to have 2 vanadium species that we'll put together, and we're going to have 2 zinc species that we're going to put together. But being in acid or base, which is what the third example will be, is going to be important. In acid, you can only have H plus and water. You can add as much of those as you need to. However, H plus and water is what you need to add. So let's see how this works. So first what we want to do is just put the half reactions together. And again, you don't have to know which is being oxidized and reduced. You just want to put the similar species together. So I would definitely put, for example, the zincs together. Zinc going to zinc 2 plus seems reasonable. And then we'll also put the vanadium complexes together. Now earlier in the question, I showed you that vanadium in VO2 plus 1 is a positive 5. In the second one, the VO2 plus, that vanadium is a positive 4. So notice it's going from positive 5 to positive 4. That means it's gaining an electron. The vanadium species is being reduced. And zinc here is losing 2 electrons to make zinc 2 plus, so that's why it's being oxidized. But again, you don't have to worry about it. Just put the like species together and everything should be cool when you get to the adding electrons part. We'll balance each half reaction for mass, and remember, in acid, you can only have H plus and water. So the zinc is good to go, 1 zinc on each side, that's not a problem, but the vanadium is definitely messed up. The reactant side has 2 oxygens, VO2 plus 1, and the product side has 1 oxygen, VO 2 plus. So we need to add some oxygen containing species. Now between water and H plus, the only thing with oxygen, of course, is water. So let's start off by adding water to the product side. All right, no problem. But now we have H plus on the product side and no H plus on the reactant side. So in addition to water, you can add H plus ions. This would be the balanced mass reaction for this half reaction. 2H plus VO2 plus 1 makes VO2 plus and a water. So you want to add the water to the oxygen deficient side. You add H plus to the hydrogen deficient side when you're balancing these. We need to balance the half reactions for charge, and this is where we're going to add electrons. We can only add negative electrons at this point, but using this, we can make this happen. So zinc going to zinc 2 plus. Zinc 2 plus is more positive. We're going to add electrons to the more positive side. If we add 2 minus 1 electrons, that'll balance that positive 2, make the whole product side a charge of 0, and that's what the zinc metal is. So 0 to 0, this reaction is now balanced for charge. The vanadium will do something similar. Now, let's break down the product side first. VO2 plus has a positive 2 charge, and water has no charge. So the whole product side is a positive 2. And if you ignore that electron for just a little bit, VO2 plus 1 is a positive 1 charge. 2H plus, that's 2 times plus 1, positive 2. So you've got positive 2 from the H plus and a positive 1 from the VO2 plus 1. Positive 3. Well, positive 3 on the reactant side does not balance positive 2 on the product side, so we're going to have to add 1 electron to make them balance out. And then if you look at it, minus 1 from the electron, plus 2 from the hydrogens, plus 1 from the VO2 plus, all of that gives you a positive 2 charge, which is what you have on the reduced part. So this is how it works. You just try and add electrons to the more positive side, and hopefully then that will be enough to make everything balance out. You want to multiply by an appropriate factor so that when you add the oxidized and the reduced species together, the electrons don't show. All right, that's pretty important in chemistry. So we'll leave the zinc alone, but the second reaction, we're going to multiply that whole thing through by 2 because we want 2 electrons, not just 1 electron. That way the zinc 2 plus 2 electrons, those electrons will cancel the 2 electrons in the vanadium part and everything will be cool. So I multiplied all of those through by 2 in order to get that answer. So the final step is just adding them together. You're going to have the zinc, you're going to have H plus and VO2 plus 1, and that's going to make zinc 2 plus VO2 plus and 2 waters. And again, you are welcome to check these, make sure they're balanced for both charge and mass, because it's both really important. You have just balanced a reaction in acid. Remember, in acid could mean things like pH less than 7, could be an actual pH number. All of those things would be legit. And again, in acid, only add H plus and water. In this question, we're being asked how many electrons are flowing between the tin and the silver plus. So on the reactant side, you can see we've got tin metal and silver plus ions, and apparently electrons are flowing between those. On the product side, you have tin 2 plus and silver. You can look at tin or silver. I think doing the tin is a little bit easier. Tin is going from a tin 0. Tin solid means tin of a 0 charge. It's going from a 0 charge to a positive 2 on the product side. So that means here that tin is losing 2 electrons to become tin 2 plus. But just because we think they've lost, we should also check the part that's being reduced, and that's silver plus going to silver. So each silver plus needs 1 electron to become silver metal, and there are 2 of them, so 2 electrons are needed to make 2 silver plus turn into 2 silvers. The operative word here is 2, all right? As long as you see that there's 2 electrons being transferred, that's the important part. Usually one species, the oxidized or reduced, is easier, In this case, tin going to tin 2 plus, yeah, it definitely is going to need to lose some electrons, and 2 electrons specifically. And when you think about the stoichiometry, that's why there's the big 2's. It takes 2 silver pluses to gain 2 electrons to make the 2 silver metals. In this reaction, we're going to take permanganate, MnO4 minus 1, and a peroxide, HO2 minus, and we're going to turn that into manganate, which is MnO4 2 minus, as well as oxygen. But also notice that this one claims that it's in base. So in a base system, you have actionable items of hydroxide and water, but you don't have H plus in water, which is what we saw in the acid. So we'll talk here in this section about how to conquer the basic solution redox balancing questions. And it's not too bad. The first way I'm going to show you is actually pretty quick. The second way, which is a little bit longer, is a way that I use honestly quite a bit because I've never felt super good about balancing things in base. But my longer version, my longer process way will work, and it's something just to keep in the mind. Remember, a base could be a pH greater than 7, so I could say balance this reaction in a pH of 8.90, and that would mean balance it in a base. That's totally normal. Okay, so first up is combine the like species. Let's combine the 2 manganese species as well as the oxygen species. So for the first one, it's peroxide going to oxygen. Peroxide is a special form of a charge on the oxygen. It's a -1. And oxygen is O2, is elemental oxygen. The elements are usually neutral. They don't have positive or negative charges. So we'll put those 2 together. We'll also put the 2 manganese together. Now, permanganate, the first one is a +7. We looked at that earlier. But the other one, manganate, if you figure out its charge, oxygen's almost always -2, and there's 4 of them, -8, but it has to have an overall -2 charge. That means that manganese is a +6. So if you look at this long enough, the manganese is going from +7 to +6. It's being reduced. On the other hand, an oxygen that's -1 to an oxygen of 0, that would be something that's being oxidized. Next up, balance each half reaction for mass. The manganese is great. 1 manganese and 4 oxygens on both sides, no problem. But the other one is not balanced. Like, for example, the reactant has an H and HO2 minus 1, and oxygen, of course, has no H. So what you want to do is you want to add water to the hydrogen deficient side. There's like 2 hydrogens per oxygen. And then you want to add hydroxide to the opposite side. So at the end of the day, when you balance this one out, you'll end up with 1 water on the product side and 1 hydroxide on the reactant side. And this leads to a good rule of thumb. If you have a hydrogen deficient side, add water. If you have an oxygen deficient side, i.e. HO2 minus didn't have as much oxygen as O2 and water, then you add hydroxide. So hydroxide to the side that needs oxygen, water to the side that needs hydrogen. And if that works for you, this method is better. It's quicker, more efficient. But if it doesn't work for you, I'll talk about my alternative method here in a little bit. All right, the next part is to balance the half reactions for charge, and you can only add negative electrons at this point, remember. So for the hydroxide and peroxide side, each of those has a -1 charge, so -2 on the reactant side. And the product side initially has no charge. O2 is neutral, water is neutral, so we don't have any charge. So -2 on the left, 0 on the right, that's not balanced for charge. We can only add negative electrons, so we'll add 2 electrons to the product side, and now the charge will be the same on the reactant and the product side. Both of them will be -2. We'll do something similar with permanganate on the left going to manganate on the right. Manganate is -2 and permanganate is -1. So if we add an electron to there, that's going to make the -1 of the electron and the -1 of the permanganate equal the -2 of the manganate. So that would be the way to balance this out. And again, at this stage, you should have something that's losing electrons and something that's gaining. As long as you do that, you've got this redox system down and you should be good to go. The next step, we want to multiply one or both reactions by some factor in order that we end up canceling out the electrons. You don't want to show electrons in your final reaction. So we'll leave the first part right alone, the hydroxide and peroxide part. But the second one, let's multiply that through by 2. So that would be 2 electrons plus permanganate, and that equals manganate, MnO4 minus 2. Notice there's 2's in front of each of those once again. That's just to make the electrons cancel out. So when all is said and done, you add those half reactions together, the electrons will cancel out. You don't want to show them and stuff. This is what you're going to end with. Peroxide, the HO2 minus thing, plus hydroxide plus 2 permanganate makes oxygen plus water plus 2 manganate. And this is how things flow, if you will, in the basic solutions. If the system we just went through works for you, where you add water to the hydrogen deficient side and hydroxide to the oxygen deficient side when you're balancing basic solutions, you are good to go. However, I've oftentimes had problems trying to figure out how this all works. The hydroxide and water thing is just really weird to me. So an alternate way to balance these reactions, which does work all the time, is you first want to pretend like you're balancing the reaction in acid. And then after you get it all together, you can neutralize the acid with base. And I'll show you what this means here in a little bit. So let's go back to the permanganate and peroxide, the HO2 minus, making manganate, MnO4 2 minus, and oxygen. So as before, we'll separate them out into half reactions. No big surprise there. You want to then make sure that the atoms are balanced on both sides, but we're going to pretend that we're doing it in acid right now. Now, acid's usually really easy, I'll be honest. So what we're going to do is pretend we're in acid, and at the end we will come back and figure out what would be in base. So if this was acid, HO2 minus to O2, well, you can probably see that the reactant side would be just H plus. The manganese you don't have to do anything to, because 1 manganese and 4 oxygens on both sides. But the oxygens, oh goodness, yes. But the oxidized part, the peroxide and oxygen, we have to do something there. And what we would do if this was acid is just add an H plus, because then you see you got 1 H and 2 O's on the reactant side. That makes 2 O's and 1 H on the product side. So the whole process will work. It's a lot easier when it comes to acid. We can just see right away that the product side needs an H plus, add it in, good to go. Next step is to balance the half reactions for charge. We can only add negative electrons at this point. So the peroxide has a -1 charge. The product side is oxygen, which is 0. H is +1 here. And you can see that O2 and H plus, that has an overall +1 charge. And that's a lot different from the -1 on the peroxide on the reactant side. So if you add 2 negative electrons to the product side, now you've got O2 0, H plus and 2 minus, so -2 + 1 is going to give you the same charge you have for HO2 -1. So we're going to add electrons as products in this step. The other one you can make balance by adding an electron to the reactant step. So the product, manganate, MnO4 2, has a -2 charge, and on the reactant side, the permanganate, MnO4 that has just a -1 charge. So we need to make the left-hand side more negative. So we're going to add a negative electron to the permanganate. That'll be -1 and -1, or -2, and that's going to be the charge on the MnO4 2-. So we're going to add an electron. Now notice at this point that the peroxide, the first half reaction, that's losing electrons, so that's being oxidized. And the second one down here, the permanganate going to manganate, that thing's actually gaining electrons, so it's being reduced. You don't have to worry about initially if something's being oxidized or reduced. Just kind of put the like species together, follow these steps, and it should come out naturally. We're now going to multiply the half reactions by some factor in order to make sure that when we add them together, the electrons will cancel. So in the oxidized species with the peroxide, you've got 2 electrons as products, but the manganese example only has 1 electron as a reactant. So we need to multiply the permanganate manganate by 2 in order to make sure the electrons will cancel. So we'll have 2 electrons on the reactant side now, and that's going to cancel the 2 electrons on the product side for the HO2 thing. Let's add these half reactions together. The electrons will cancel out. Anyway, you end up then with HO2 minus plus 2 permanganates, and that goes to oxygen gas plus H plus 2 manganates, MnO4 minus. And this equation is now balanced, but the pH is for pHs less than 7. So this reaction is balanced for acid. It has H plus. H plus in water means acid, but we wanted our system to be in base, pH greater than 7. So at a pH greater than 7, you'll still have water, but the H plus will be turned into hydroxide. So what we're going to do to make sure this acid reaction is turned into a base, you can add a hydroxide for every H plus that you have. And in addition, if you add something to the product side, you have to add the same amount to the reactant side and vice versa. So in this reaction, as written, there was only one H plus. So we're going to add one hydroxide to both the product side and the reactant side in order to make this all work out. So an H plus OH minus on the product side will be the new thing to look at. And again, you'll also have a hydroxide on the reactant side. If you add it to one side, you have to add it to the other. The H plus and the OH minus will combine to make water. So you can see that down there in the bottom, all of a sudden the water popped in. That's the H plus OH minus. But there's still a hydroxide on the reactant side, because remember, you add it to one side, you have to add it to both sides. So the final reaction, HO2 minus plus 2 permanganate plus hydroxide, goes to oxygen plus water plus 2 manganates. So hopefully it will give you the same reaction as all the balanced ones you've been doing. Just kind of keep this in the back of your mind. So if you follow these rules, you're good to go. I like the neutralize and acid option, truthfully. Once in a while, I don't need to. Once in a while, I can do the base ones on my own. But if you ever need to, it's a pretty cool way to figure this out. Okay, so here's some tips for balancing redox reactions. First of all, you've got to know the pH. pH is less than 7, you can have H plus in water. pH is greater than 7, you can have hydroxide in water. So you've got to know what pH it is to make sure that's going to happen. Acidic pH is H plus in water, basic pH is hydroxide in water. When you're adding things, you never want to add O2, oxygen atoms, oxides, or for that matter, hydrogen, H2 or H plus H atoms. You just want to add what's appropriate to your pH. So again, pHs that are acidic, H plus in water. pHs that are basic would be water and hydroxide. You want to make sure all the ions have the right charges on them, super important. And again, you can always check yourself at the end to make sure the reactions are balanced for mass and charge. All good chemistry redox reactions will be balanced for mass and charge. So now that we have the balancing of redox reactions all figured out, what we can do now is start applying them to actual practical conditions where we can enact a chemical change through the transfer of electrons. And the best example probably of this is if you put reactants together and they start reacting. It's like a battery that works, all right? And those are important. And again, they call batteries that work essentially galvanic or voltaic. Their product favored electrons start flowing. So as an example of this, in the upper right hand corner, you can place a piece of zinc metal, which comes as a strip, in a copper 2 plus solution. And copper 2 plus has kind of that cool blue color. And what happens is right away the chemicals start reacting. Zinc gives up its electrons easily. It's oxidized. Copper 2 plus loves to take those electrons to make copper metal. Copper 2 plus likes to be reduced. This is what they call a direct redox reaction. They're very high yields, all right? You have a very high turnover. Zinc goes to zinc 2 plus and copper 2 plus goes to copper metal, which is really neat. However, you don't have any control over the reaction. So you start putting the reactants together and you're like, oh crap, I didn't want to put those together. Well, you could take the piece of zinc out, but there's no other way to stop the reaction. So direct redox reactions do have their use, but we're going to talk about the indirect redox reactions, i.e. batteries, more in just a sec. This reaction on the right shows a similar reaction, but now it's copper metal reacting with silver plus ions, and copper 2 plus is made and silver metal is created. And this is also a reaction which is going to happen. It's going to be spontaneous. Its delta G Gibbs free energy value will be negative, and people call this galvanic cell or voltaic cells, same thing. So in this kind of reaction, you also have something spontaneous, but the difference here is that now we have a control over how reactions will actually happen. Like if we wish to stop it, we can, or we can just let it go, either way. So in this reaction, notice that copper is going to copper 2 plus. So copper is giving up electrons. And as copper gives up electrons, the electrons now are going to flow in a wire. So in red here, I have the directions that the electrons will travel. And notice that there's a negative and there's a positive. Well, electrons are negative. They want to get away from the negative side and they want to go towards the positive side. So electrons are going to go from the copper to the silver piece of metal, which is in solution. And they're going to go right down the metal because metals transfer electrons, no problem. And it's going to turn the silver plus, which is in the solution, it's going to turn the silver plus into more silver metal, which is pretty cool. That's what happens when the electrons go through the silver to the silver plus. It makes more silver metal. So you can imagine then that the silver metal is kind of filling up here on the bottom. Well, the problem here is that as silver plus goes away, you can't just add silver plus. It has to come with something different. And it most likely is going to be a nitrate ion. Well, as nitrates build up, you get more and more negative nitrates running around. So that kind of stops chemical reactions from happening. So what scientists do is they put between the two sides, they put what's called a salt bridge. Salt bridge is usually like an agar or essentially like a type of seaweed kind of holding U-tube thing. And what happens is negative ions will flow from, in this case, the silver side to the copper side. So the negative ions are flowing from the right to the left, if you will. And that's a good thing because as the copper gives up electrons, you have more and more copper 2 plus. So you need more negative ions, i.e. nitrate, this time from the silver side, in order to balance that out. So here's what's cool about this. Electrons are going from the copper to the silver through that kind of top part right there. And then nitrates, which are negative, are flowing from the left to the right. And then you have more electrons going there. This, my friends, is like a type of electron highway. Electrons will travel from the copper to the silver, and then negative nitrates, which are a source of negative electrons, will flow through the salt bridge from the silver side to the copper side. So you've got electrons constantly moving around and around and around. And this is now called an indirect circuit. You're able to control the chemical reaction. You can turn it on and off as you want. You could put little light bulbs on the top to see the electrons are flowing. You could have an on-off switch, which is cool. It's really fantastic. So in this kind of cell, which is what they call a galvanic or voltaic cell, which just means electrons start flowing, electrons will flow from the oxidizing site, this part that's losing electrons. So that's why that site gets a negative charge. It's called the anode. And electrons will flow from the negative anode to the other side, which in this case is positive. They call that the cathode. So electrons you see are flowing from the anode to the cathode, which is pretty cool. So that's what happens in a galvanic cell. And again, the advantages of this is that chemists can control it. When you put the zinc metal directly in the copper 2 plus, the reaction just went crazy. And you could do the same thing here. You could put copper metal in silver plus, and silver would start forming, and blue copper 2 plus would form, but you wouldn't have any control over it. This way, with this salt bridge and the wires and stuff, you can actually control the electron flow, which allows you to control how current is distributed, and that's the idea behind a battery. So in this question, we want to find the reducing agent in the reaction. And reducing agent and oxidizing agent, for that matter, always refer to reactants. So the answer here will be nickel or silver plus. It will certainly not be the nickel 2 plus and the silver because those are products. Also, we know it is a redox reaction because nickel is changing charge as it goes from reactant to product. Nickel's going to a positive 2. Silver plus is becoming less positive as it goes goes to silver. So reducing agent, you have to remember, reducing agent means that it's being oxidized. All right, so we're looking here for the species that's being oxidized. Oxidized, lose electrons. Oxidized, that means something's becoming more positive. And if you look at this long enough, nickel is going to nickel 2+. It's becoming more positive. It's losing electrons. Nickel is being oxidized. And something that's oxidized, you guessed it, is the reducing agent. So reducing agent means oxidized. Silver plus is being reduced to silver. That means silver plus is the oxidizing agent in this reaction. Keep those in mind. They can get confusing, but it's nothing you can't handle. There are different expressions that might help you in these next areas, and they're kind of silly, and some people like them and some people hate them, so don't feel like you have to use them. But anyway, if they do help you, I think it's worth talking about. First one is a red cat. Reduction occurs at the cathode. So if you have, for example, copper 2+ going to copper, that would be the cathode, because copper 2+ is gaining electrons to become copper metal. On the other hand, an ox would be oxidation at the anode. So zinc going to zinc 2+, zinc is being oxidized. That would mean that zinc would be at the anode. So reduction at the cathode, and zinc would be oxidizing at the anode. And more importantly than anything, just note that reduced and cathode, they both begin with consonants, while oxidized and anode both begin with vowels. Now, if you haven't thought about vowels and consonants for a while, I understand. The vowels are A, E, I, O, U in the English language. And notice that ox and an both begin with vowels. So they go together. On the other hand, the consonants, which are everything but the vowels, are both R and C in reduction and cathode. That's how I usually think about them. But some people like the red cat and the an ox, which is fine too. And finally, oxidation means reducing agent and reduction means oxidizing agent. So just remember that. If you see the agent, it's like the opposite of what it's trying to imply. I hate it, but again, I'm just the messenger here. So something that's being oxidized is the reducing agent. Something that's being reduced is the oxidizing agent. Salt bridge is just some kind of material that allows the ions to flow through. The most important ions for us is it's going to flow from the cathode to the anode. You do have a little bit of counter ion moving the other way, but we're not going to worry too much about that. But the idea is that as the silver plus becomes silver, you no longer have as much positive charge at the cathode. So those negative anions are going to go over to the other side, the anode. They will take the place then and help out the copper 2+ ions which are forming. Copper 2+ needs an anion to make it balanced. It just is all about keeping everything neutral. And if you do this, the important part is that electrons literally flow from the anode to the cathode, and then anions flow from the cathode to the anode through the salt bridge, which is pretty cool. We used to make salt bridges when I was in graduate school, and again, we used a type of a seaweed and agar kind of stuff, and you have to let it soak for a while, and it kind of stunk as I remember, but again, they're not too hard to create, and they do keep the electrons flowing, which is what you want in these kind of systems. Instead of drawing out an extensive anode-cathode combination, a lot of times people will use shorthand notation. And this is specifically the shorthand notation for galvanic cells. Galvanic or voltaic cells are the ones that start working when you put them together. They're spontaneous product favored. So the copper 2+ and zinc reaction going to zinc 2+ and copper metal can also be written in this little piece down there. And at first this is a little weird, but it's not too bad once you know the rules. First of all, the main rule is that electrons always flow from left to right. So just like people read in the English language from left to right, electrons flow left to right. So what that means is zinc going to zinc 2+, that's going to be the oxidizing part. Zinc is being oxidized. And then copper 2+ and copper, that means copper 2+ is going to gain electrons to become copper metal. So electrons come from the zinc side and they go to the copper side. That's kind of what that implies. Now, as something is being oxidized, it's also known as the anode. Remember, ox and anode, anox, or they're both vowels, whatever you want. The anode's on the left, and something that's being reduced is at the cathode. So reduced cathode, red cat, right? They go together, whatever consonants, whatever you want. So anode on the left, cathode on the right. Now there's single lines and double lines. Single lines just imply a phase boundary. So for the zinc, that would mean going from a solid zinc to an ion, an aqueous ion. So that's the phase boundary. You're changing what it looks like. Copper 2 plus going to copper is the same. You're going from a solution to a solid on that phase boundary, but same idea. The double line in the middle implies a salt bridge. That's where the ions are going to have to flow from one side to the other to keep everything electrically neutral. So if you understand how all of this works, it is a lot more convenient. You can write this in, say, Microsoft Word. You don't have to draw out the elaborate oxidize, reduce, salt bridge, all that kind of stuff. This is the shorthand version, which can be really helpful when talking to colleagues. Fat cat is another expression that's sometimes used in this area. Electrons flow from anode to cathode. From anode to is fat, cathode. Anyway, I don't know if you like any of these things. I think I just like showing pictures of cats. You know, it kind of cracks me up. Anyway, weird sense of humor in your instructor. But anyway, fat cat can help you learn this stuff too. So let's describe this reaction using our knowledge of what shorthand notation is all about. And you can see there's copper and copper 2 plus on the far left. And then starting in the middle and going to the right, you've got chlorine, Cl2, going to chloride. And there's also platinum solid on the far right. So let's make sense of all of this. Well, first of all, electrons are flowing from the left to the right. All right. So that means copper is going to copper 2 plus, and in the process, 2 electrons are created. The copper 2 plus concentration, the moles per liter, is 1.0 moles per liter. So the 1.0 moles per liter tells you the concentration. That'll be important to us. We'll talk about that in a little bit. Then you've got the salt bridge on the other side that separates the two compartments. And on the other side of this, you've got chlorine going to chloride. Remember, electrons are always flowing left to right. So chlorine, Cl2, is gaining 2 electrons to become 2 chlorides, all right? And along the way, the chlorine gas, which is a gas, by the way, it's one of the red elements if you have a periodic table that shows the phases. Chlorine is a gas at 1.0 atmospheres. That's the pressure of the gas. And the chloride on the other side too is at 1.0 moles per liter. So those are the concentrations and the pressures of the gas. It's the gas that's accepting the electrons to make chloride in this case. Now, on the chlorine side, chlorine's a gas, chloride is a solution. You don't have any way to transfer the electrons from the copper side into the chlorine unless you put a platinum electrode in. And it's very common to use platinum, sometimes nickel, palladium, stuff like that. They're usually pretty inert metals that will transfer your electrons in. So the platinum is allowing the electrons to go from the chlorine gas to the chloride. That's why it's included right there. Most of the examples we've seen have had a metal as either reactant or product, but in this case, chlorine going to chloride, you don't have a metal. You need a platinum electrode to transfer those electrons in. In this question, we want to know what species is being oxidized, and it shows a shorthand notation. All right, well, oxidized means losing electrons, so we want to figure out what species is losing electrons. And remember, electrons move from left to right in the shorthand notation. So that means zinc is going to zinc 2 plus. Zinc metal, zinc solid, is going to lose 2 electrons to become zinc 2 plus. Zinc metal is the part being oxidized. All right, electrons are going left to right. The gold plus, which is Au plus, by the way, the gold plus is going to accept the electron or electrons to make gold metal. So gold plus is gaining electrons, it's being reduced, but the zinc metal is losing electrons to become zinc 2 plus.